So you guys may be familiar with your traditional coordinate systems in R2. So the next step is to continue to think about coordinates in a higher dimension, or in R3, or three-dimensional space. So just like in R2, we had an x and a y component, in three-dimensional space, we should think of having another one. So x, y, we should add this z component, or it is a triple of numbers, a, b, and c. The Cartesian coordinate system we have still has an origin, like 0, 0, 0, and instead of the two axes of just x and y, we have the x, y, and z axis. We create this system by creating another perpendicular axis, this z axis. Remember that x was perpendicular to y in our R2 case. Z is going to be perpendicular to both of these other axes. Now, we could orient the graph any sort of way we want to, as long as we follow the right-hand rule. So the right-hand rule is we pick our first axis, which we'll call our x1, and then we'll point it in that direction, which will be this case. We curl it towards our second one, and our thumb will indicate where our z-axis should be. So the positive values of x should be where we initially had our x, the positive values of y is where we're curling, and the positive values of z is where our thumb goes. So if we wanted to orient it a little differently, like this case, this is still a valid orientation because we're going to follow the same principle. So once again, we put our x value there, and we curl up towards the y, and our z is pointing out like this because that's where our thumb is pointing. Okay? So this is your right-hand rule to be able to know where the positive values of x, y, and z should be. So suppose we want to locate a point P, A, B, C. What do we need to do? We need to move A units in the x direction, B units in the y directions, and C units in the z direction. So let's say we were asked to graph the point 2, 1, 3. Well, we have this coordinate system already set up. So right here, we have our x, so we need to go down 2. Then we need to go over 1 in the y direction, and then up 3 in the z direction. 1, 2, 3. So it would be right here in this three-dimensional space, and that's where P would exist. You can also think of it as a little box, right? Like that. And then this part is just going up to the P spot. And it can go over like that, or should line up with the Z. So that's how you'd graph a singular point on the three-dimensional coordinate system. So suppose we were asked to graph a function where z was just equal to 3. Now, we have our coordinate system that we've set up, and pretty much only specification we have is that z needs to equal 3. X and y can be anything we want. So we have our z components, we have our y components, and we have our x components here following this diagonal line that we're trying to represent. This orange square would be the graph of z equals 3 because we have the point z equals 3 right here because z starts at 0 here, and we had to go up 3 in the z direction, and x and y could be anything else. So that's a pretty easy one to just graph. Now, if we made this a little bit more difficult, we could ask ourselves, how do we graph y equals x squared? Well, you may be like, okay, in the 2D system, I know how to graph that. That's a parabola. Well, let's just think of it as a parabola for now, and let's ignore this z component. Now, we know how to graph a parabola, so we've got our point right here, and then we just need to create our parabola, like that, going in each direction. Now, the z, there's no specification. So whatever satisfies this parabola, if you pick any value for z, it'll also still satisfy this equation. So it's just a parabola moving up and down the z-axis. So you can just pull it up all the way here, all the way here, all the way here, all the way here, and you just continue, and you can think of it as parabola, and then you'd also connect to the bottom. And so you have what looks like a parabola, but moving up and down all the way on the z-axis.